Okay, so, all right, here we go. I didn't realize I'd already started recording. That's okay. All right, everybody. So, what we're talking about in section 14.6, Kelsey, is we are going to look at using integrals to calculate mass or centroids, which is like basically the geometric center of stuff, okay? So when we talk about center of mass, we're talking about some object, whether it's one-dimensional, two-dimensional, three-dimensional, such that when you put a sharp fulcrum or pivot or whatever somewhere on it, at that center of mass location, that object is perfectly balanced. You know, in some objects, it's very easy to find the center of mass if you have symmetric density or even constant sort of density. Chances are it's going to be right in the middle or easily figured though. But if you have irregular shapes with variable density, then it may very well be a little bit more challenging. But if we have some algebraic rules which define the edges of our object and for the density, then with some calculus, you know, we should be able to calculate. Now, the problems can get to be pretty hairy and involved, and we're just going to look at some basic ideas this evening. But just to understand that you're going to have some homework problems that might take a minute or two to do, okay? Understand that. That's just the nature of the beast for calculus, right? Now, let's just kind of review something that you probably already know, is that when we're looking for the center of mass, like I said, we're looking to see where can we put the pivot so that the system is balanced. So in the one-dimensional case, we might just have simply a rod with two masses located at two locations along the line. And the way we want to do it is such that the one mass times the distance from the center is going to be the same as the product of the density, the distance times the mass for the other one with respect to that center. So that's why we would say mass times distance is equal to mass times distance. And then solve for that location. So we might say, for example, that, you know, this is at x bar. We may not know what x bar is. That the location for M1 is at x equals x sub 1. And the location for M sub 2 might be at x sub 2. So what we would do to find the location for x bar is to basically do the weighted average of those x coordinates. So x1 times m1 plus x2 times m2 divided by the total mass m1 plus m2. And that will give us the coordinate for our center point. So it's just the weighted average of the locations, right? So this is basically reiterates what I just told you. And of course, that's only for two masses. If you have three or more masses, you just take the sum of those products of the masses times those x coordinates. Sometimes setting up your coordinate system a certain way will make your calculations easier. You'll have the chance to practice this in the homework. Here's another example here. We've got this 160 kilogram gorilla. Is that a gorilla? Is that a gorilla? I know there's a distinction between like gorillas and apes and monkeys. I think that's a gorilla. And you got an 80 kilogram man over here. Now the gorilla is 4 units to the left of the origin. Here's the origin 0, at least according to this coordinate system. So here, the gorilla's at -4, the man's standing at 2. So where exactly should we put that center point? So all we need to do is just do a quick little back of the envelope calculation. The mass of that gorilla is -160, and he's standing at x equals -4. And that's positive 160, by the way. So 160, and then plus the weight of the man, which is 80 kilograms times his location at 2, and then divided by the total mass, 160 plus 80. So this is what, -320, -640, so -640 plus, and 2 times 80 is 160. And divided by the total mass of, what is that, 240. Now, -640 plus 160 is, what is that? Is that 480? So 480 divided by 240, and that's equal to 2. So that's going to be the coordinate for your center. In other words, the balance point right here at x equals 2. Actually, that's going to be negative, huh? That's negative. I forgot my minus sign. So minus -2 for the balance point. Okay, so 2 units from 0 going toward the gorilla. Should make sense anyway because the gorilla is so much heavier than the man. All right, here's another example here. Apparently we've got 4 masses here at these 4 locations, and we want to find the center of mass. So like I said, you just take the x coordinate times the mass plus the x coordinate times the mass plus the x coordinate times the mass plus the x coordinate times the mass divided by the total mass, and in this case it worked out to be 1/60. I'll let you check that, unless you really want me to do it. Otherwise, I'm moving on. Now, if your masses are not necessarily discrete, in fact, if you have a continuous sort of mass with a variable density, then it becomes a more complicated problem. And this time we would have to use some calculus to figure out what is the moment divided by the mass. That'll give you your center point. So the idea is to chop that strip up into a bunch of tiny little pieces with delta x, and then to calculate the mass of each of these little chunks, where the density is approximately constant, will just be the density times delta x. And then you add them all up, but don't take the limit as delta x goes to 0, and then you've got your total mass. So all you need to do is just integrate over that bar the density function in order to get mass. And then you also need to calculate the moment, which is just basically x times the density. And then take the moment divided by the mass in order to get your center of mass, or aka the balance point. So We typically use capital M to indicate the moment. And it's just going to be the variable x times the density integrated over that rod length. And here, of course, is the mass, little m. And then the balance point is going to be the moment divided by the mass. So here, let's do an example here. Example number 2. Example number 2, suppose a thin 2-meter bar is made of an alloy whose density is given by 1 plus x squared. See, I can't talk and write at the same time. 1 plus x squared on the interval from 0 to 2. The units are in meters. Find the center of the mass of the bar. So, center of the mass of the bar, just calculate the moment. Is going to be integral from 0 to 2 of, now, x times 1 plus x squared. That's your x times your density, dx. So that's integral from 0 to 2 of x plus x cubed. So they'll give you what? 1/2 x squared plus 1/4 x to the 4th power. Evaluate it from 0 to 2. Plug in 2 for x. You got 1/2 times 4, which is 2, plus, and then 2 to the 4th power is 16, divided by 4 is 4, so you end up with 6. So 6 is the moment. And then calculate the mass, integral from 0 to 2 of this, the density function. And you get x plus 1/3 x cubed on the interval from 0 to 2. And you get 2 plus 8/3. But 2 could be written as 6/3. 6 plus 8 is 14, so you get 14/3. And then to calculate the center, x bar, it's going to be moment divided by mass. You get 6 divided by 14/3. Or in other words, 3 times 16 is 18 over 14, which reduces to 9/7 or 1.4. So if no, that's not 1.4, sorry about that. But it's 9/7. What does that work out to be? About 1.29. 1.29. As in 1.29 meters from the edge that is the least dense. Okay. So there's just a simple exercise in calculating the center of mass. Now let's talk about finding center of mass for a two-dimensional thin region. Now the idea here is this. Now it doesn't really exactly work in nature, in reality, but imagine that you have an infinitely thin plate with variable density, kind of like what you see there. So you can kind of see the darker part here, so maybe this part is more dense than up here. And the question here is where is the center of mass with coordinates x bar, comma, y bar? Well, this time we have to use double integral. But if you understood it for the one variable sense, then it's not too hard for the two variable sense. So what we need to do is to calculate the moment with respect to the y-axis and with respect to the x-axis, and then for each one of those divide by the mass in order to get x bar and y bar. So for example, X bar, meaning the x coordinate of your center of mass, is going to be the moment with respect to the y-axis. Why? Well, you take a look at the distance from the y-axis out to your point. That's going to be, well, y, right? Horizontal distance. And then so you're going to integrate that y times the density in order to get your moment with respect to the y-axis. And then divide that moment with respect to the y-axis by the mass in order to get x bar. So it's a little bit confusing at first, just to understand that the moment with respect, and that distance is actually x, not y, I should have said x. So basically what you do is you take the double integral over that region of x times the density in order to get your moment with respect to the y-axis. Then divide by the mass in order to get x bar. And to get y bar, you calculate the moment with respect to the x-axis. So you're going to be integrating the y times the density over the entire region, and then divide by the mass. Divide that moment by the mass in order to get y bar. So you have 3 calculations that you could potentially do. Fortunately, a lot of the problems that you end up doing, though, you take advantage of symmetry, so that it could be that one of the moments is going to be 0 or some other convenient value, because of the fact that it could be that the density is symmetric with respect to the y-axis, for instance, in which case x bar is going to be equal to 0. So that just leaves you with 2 integrals to evaluate instead of 3. But, you know, there are going to be some problems where you have to crank out 3 double integrals. Let's do an example. Number 3 on page 1047. Now, when they ask for you to find the centroid, they ask you to find the centroid is basically the geometric center. So imagine that you've got this 2-dimensional object with density of 1. Now, take advantage of symmetry. It turns out for this particular object, this region, that there's symmetry with respect to the x-axis. So y bar is 0. So now you just need to find x bar. So you need to compute your moment with respect to the y-axis, so, and then calculate the mass. Now the mass is actually going to be the area, because the mass, you're integrating the density function, but the density is 1, so the net result is just finding the area anyway. So let's go ahead and set this up. Now, the 2 functions which define this region are given by e to the negative x minus 1/2 and 1/2 minus e to the x. So let's go ahead and calculate the mass, which is the area, by the way, in this case. Now, we could integrate with respect to y first. And y is going to vary between 1/2 minus e to the negative x and e to the minus x minus 1/2. So we're going up this way. And then x is going to vary between 0 and natural log of 2. Plus. And this isn't too hard of an integral to calculate. You know, so integrate with respect to y, of course, that'll just be e to the negative x minus 1/2, and then minus 1/2 minus e to the negative x dx. 0 to 2. A little bit of work here. So you got e to the negative x plus
e to the negative x is 2 times e to the negative x.
That's still bounded to the natural
Natural
log.
log of 2, thank you. And then minus 1 dx. So you get what? Negative 2 e to the negative x minus x. Evaluate it between 0 and 2. Now you plug in 2 for x. What? E to the negative 2 minus 2, and then plug in 0. When you plug in 0, you get what? Just negative 2, huh? Now, I think the 2's cancel, don't they? Leaving you just with what? Well, you get negative 2 minus negative 2. So I'm off by a negative sign. What does that work out to be? So I'm off by a negative sign. So that's supposed to be 1 minus natural log of 2? Oh, sorry about that. That was natural log of 2. Sorry about that. Natural log of 2. Let me pull out my... That's why we do our work in pencil, don't we? Because those little mistakes are going to happen. So let's try this again. Replacing x by natural log of 2. You got negative 2 times e to the negative natural log of 2 minus natural log of 2. And then plug in 0. And when you plug in 0, you got minus negative 2. Remember, e to the 0 is 1. So you'll have plus 2. Plus 2. Now, e to the negative natural log of 2 is what? That's e to the natural log of 1/2, huh? Which is 1/2. So you get this whole thing right here is negative 1. So you get negative 1 plus 2, which is 1, and then 1. So you get 1 minus natural log of 2. That's the value of the area / mass. Now, you calculate your moment with respect to the y-axis. Now, you have to do the double integral of x dy dx. Now, remember, y varies between 1/2 minus e to the negative x and e to the negative x minus 1/2. And x is going to vary between 0 and natural log of 2. All right, so we know how to evaluate double integrals. Let me just cut to the chase. And this works out to be 1 minus natural log of 2 minus 1/2 natural log squared of 2. Now, at this point, it might be convenient to round each of these numbers to some decimal. So 1 minus natural log of 2, I guess, worked out to be about 0.307. The 1 minus natural log of 2 minus 1/2 natural log squared of 2 was approximately equal to 0.067. The x bar is going to be approximately equal to, and it's approximate because I've already rounded the moment and the mass. Well, hold on here. Let me say that this is exactly equal to the moment with respect to y divided by the mass, and then that's going to be approximately equal to 0.067 divided by 0.307. So what does that work out to be? About 0.217. So 0.217 then would be the x-coordinate of the center of mass right here. So 0.217 comma 0.
would be that center. Well, because of the fact that this has a density of 1, we're finding the centroid. So this, the geometric center, or the centroid, has coordinates 0.217, comma 0.
All right. Take a look at example 4. Now, example 4, find the center of mass of the rectangular plate where x goes between -1 and +1, y goes from 0 to 1, has a density 2 minus y. There's the density there. Like I said, a lot of these problems, you could take advantage of symmetry to at least cut down on your calculations. So if it has a density being equal to 2 minus y, then this has symmetry with respect to what? Or does it? Well, it's only a function of y, isn't it? Doesn't matter what x is. So the x-coordinate of the center of mass is going to lie somewhere on the y-axis. Huh? So it's just really a matter of now finding the y-coordinate of the center of mass. So now you know what you need to do to find y bar. You get your moment with respect to x divided by the mass. So you've got two integrals to evaluate. So calculate the mass first, or you can do it second, it doesn't matter. And so you're going to evaluate the double integral of the density 2 minus y over this region. Now, x is going to vary between -1 and +1. Y is going to vary between 0 and 1. We can go ahead and integrate with respect to y first. Y goes from 0 to 1. And then integrate with respect to x. X goes from -1 to +1. All right? And I guess that works out to be a total of 3. And then calculate your moment with respect to the x-axis. So it means you're going to do the double integral of y times the density. And y goes from 0 to 1. X goes from -1 to +1. So it's a slightly different integral with the, it has a different integrand. Limits of integration are still the same though. So you're integrating 2y minus y squared. So your first step is you have y squared minus 1/3 cubed. Evaluate from 0 to 1, and then x goes from -1 to +1. All right. So easy integral to solve. That works out to be 4/3 for that moment. Then calculate y bar is the moment divided by the mass. So that's what, 4/3 divided by 3. So that's 4/9. So the center of mass is going to be at x equals 0 and y equals 4/9. So any questions on how to calculate center of mass for two-dimensional object? So you have to calculate your moments, and your mass, and then do the divisions. Take advantage of symmetry whenever possible. Now, we are quickly going to look at centers of mass in 3 dimensions. So if you've got a warm fuzzy of how to do this in 2 dimensions, then 3 dimensions is just an extension of this idea. Center of mass in 3 dimensions is that point, analogous to the plate with full fulcrum stuff. Anyway, it's that balance point. Such that, if there were like a little ball bearing at that point and could swivel and rotate any way that you want, it wouldn't. So the calculation of X bar, Y bar, Z bar is analogous, but you have to do 3 triple integrals to get the moment, plus a 4th triple integral to get the mass. So as you can appreciate, in class, we're only going to talk about it really. And I'll leave you for the fun of actually doing the triple integrals. To calculate the X bar, the Y bar, or the Z bar is still going to involve calculating the moment with respect to each of the 3 coordinate planes this time, and then dividing each of those moments by the mass. So to calculate X bar, to calculate the moment with respect to the YZ plane, and then divide it by mass. So basically you're going to do the triple integral of X times the density over the 3-dimensional region to get that moment with respect to the YZ plane, and so forth. So here's all the ugly details here. To get X bar, here's the moment with respect to the YZ plane, which is the triple integral of X times the density over the 3-dimensional region, divided by the mass. And same discussion for Y bar and Z bar, just integrating each of those variables times the density. And of course, the mass is just the integral of the density over the 3-variable region, 3-dimensional. Okay. Take a quick look at example 5 here. We're supposed to find the center of mass of this constant density solid cone. Hey, folks, when density is constant, then it really amounts to finding the geometric center of that 3-dimensional solid. Again, take advantage of symmetry whenever you can. Now, when we are dealing with cones, it turns out that the cylindrical coordinate system is more amenable to these calculations than the rectangular coordinate system. And there's symmetry with respect to the z-axis, isn't there? So the x-coordinate and the y-coordinate are both going to be 0, so it really comes down to how far up the cone, meaning the z-coordinate. What is the z-coordinate of that center point going to be? So we have to calculate the moment with respect to the xy plane. So that means that we would do the triple integral of z times the density, but the density is going to be constant, so let that density be k, whatever. And now, how do we set up the integral to integrate a cone? Now, the surface is given by z equals 4 minus square root of x squared plus y squared, except we're now going to switch over to the cylindrical coordinate system. So we replace square root of x squared plus y squared by r, so you have 4 minus r. So z is going to vary between 0 and 4 minus r. And don't forget your r that comes with your dv element for cylindrical coordinates. So dz, 0 goes from 0 to 4 minus r. And then you project that shape down onto the xy plane, and then you're looking at just a circle of radius 4, and theta is going to go from 0 to 2 pi. So dr, r goes from 0 to 4, and theta goes from 0 to 2 pi. Okay. So that's just a 3-variable, a triple integral for you to solve. All right. And let me just kind of cut to the chase. That works out to be, 64 thirds times pi. All right. Now, what is the volume of this cone? Yeah, we all know how to find the volume of cone. And if not, it'll be somewhere in your textbook, huh? It's 1/3 times pi times the radius squared times the height. So the radius is 4. So it's 1/3 times pi times 4 squared times the height. And what is the height of the cone? It's 4 as well. So 4 cubed, 64, right? So 64 pi over 3. So times k. So the mass, because we have constant density, it would be k times 64 pi 3. Just by using a geometric formula to find the volume of a cone. So it turns out that the moment is the same as the mass. So z bar is going to be equal to just 1. And of course, x bar and y bar were both equal to 0. So that's why 0, 0, 1 are the coordinates for the center of that solid, center of mass for that solid, with constant density. All right, let's get through example 6 and then we'll take a break, okay? Example 6. Center of mass with the variable density. This time we're going to be dealing with spherical coordinates because, after all, a hemisphere in spherical coordinates is going to be equivalent to a rectangular block in rectangular coordinates. Let's go ahead and read the setup for this. Find the center of mass of the interior of the hemisphere D of radius A, with its base on the xy plane. The density of the object is given by f of rho comma phi comma theta being equal to 2 minus rho over a. Rho, remember what rho is. Rho is the variable length from the origin out to some point in 3-dimensional space. So rho is going to vary between 0 and a. And the density is given by 2 minus rho over a. When rho is 0, so when you're right at the origin, then the density is 2. But the further away that you go from the origin, then the smaller the density is going to be. And right on the hemispheric surface, rho is equal to a. A over a is 1, 2 minus 1 is 1. So the density is 1. So the density is going to vary between 2 at the center out to 1 on the outer surface. So the question is where is the center of mass for this? Again, use symmetry to your advantage because of the fact that it's varying with respect to rho, that the x coordinate and the y coordinate is just, they're both going to be 0 in this case. So it's just a matter of finding the z coordinate, as in the distance vertically above the xy plane. So again, we need to find the moment with respect to the xy plane. That means that we're going to do the triple integral of z times the density dv over that region D. Now we want to switch over to spherical coordinates. Now Z is equal to rho cosine phi. Rho, the density, rho, when I wrote that rho, I meant the density, rho, is 2 minus rho over A. Now, spherical coordinates, the dV element is rho squared sine phi, d rho, d phi, d theta. Now, the limits of integration are going to be simple and spherical. Rho is going to go from 0 to A. Phi is going to go from 0 to 2 pi. And theta is going to go from 0 to 2 pi. So this is 0 to A, 0 to pi over 2. And theta goes from 0 to 2 pi. So that's the hardest part about this, is just setting up the triple integral. Now, it's a nice, beautiful triple integral that's not too hard to set up and solve. And of course, it takes a few lines of work to solve this triple integral. I'll let you look at the details on page 1051. But the result of this, I guess, works out to be 3 times pi times a to the 4th over 10. And you also have to calculate the mass. The mass means you have to calculate the triple integral of the density, which is 2 minus rho over A, times the dV elements is rho squared sine phi, d rho, d phi, d theta. Same limits of integration, 0 to A, 0 to pi over 2, 0 to 2 pi. And that mass worked out to be 5 times pi times a cubed over 6. So you calculated the moment, calculated the mass, and z bar then is going to be the moment over the mass, which is 3 pi a to the 4th over 10. And dividing by a fraction means that we multiply by the reciprocal. So that means we're going to multiply by 6 over 5 pi a cubed. Of course, a cubes cancel. Let's see here. You got cancel factors of 2. So what are we looking at? We're looking at 9 pi a Oh, pi's cancel too, don't they? So let me use my eraser here. Pi's cancel. So that gives us 9a over 25. If we did that right. So the z coordinate depends on knowing the radius of that hemisphere, huh? But of course, x bar and y bar are both equal to 0 because of symmetry. Okay, so the coordinates of the center of mass is going to be 0, 0, 9a over 25. Okay, so that, folks, right there is just a short down and dirty on how to calculate your moments and how to calculate your centroids and your centers of mass. When we come back from break in 10 minutes, we will talk about change of variables from one coordinate system to the next. And then after that, we'll start chapter 15. Okay, so we'll come back in about 10 minutes. Uh-oh, I hope I was recording the whole time. All right, so now we're going to take a look at what we need to do in case we have an integral where maybe the integrand is pretty nasty, but maybe the area that we're integrating over isn't so bad, or vice versa. Maybe it's a pretty simple integrand, but the limits of integration are over some really weird area that would make the integral really tough to evaluate. Sometimes the change of variables is good, just like we saw that when on the plane, for example, when we're doing double integrals, that if we're integrating over a circular region, it might be better to switch over to polar coordinates, right, Kelsey? Okay. Or in triple integrals, switching over to spherical coordinates might be better if we're integrating over a hemisphere. Because trying to do that, you're trying to integrate over a hemisphere on X, Y, Z coordinates is pretty tough. So change of variables is good. So this section, I'm not going to spend a whole lot of time here. I'm just going to point out a couple of examples, and I'm going to ask you to dig in there and read out the details, because I really want to start talking about vector fields before we leave tonight. So here's kind of the idea. Now, suppose that we were to integrate this function right. Now, we know to integrate the square root of 2x plus 1, we have to do a little substitution. Let u equal 2x plus 1. And so u now becomes our new variable. So after we do that change of variable, this is what it looks like. Instead of x, we have u. And x varies from 0 to 1. Well, after we do the substitution that u is equal to 2x plus 1. As x goes from 0 to 1, u goes from 0 to 3. Here's the square root of 2x plus 1 graph. Here's the square root of u graph. So hey, it's just a little bit simple, a little bit more simple. But imagine what that could do for us for other situations. So we're talking about either in 1 dimension, 2 dimensions, 3 dimensions, whatever. This shows the 2-dimensional case. Just doing some sort of mapping, or what they call a transformation from, one region to the next by using some rules. We all a lot of times use u and v as the variables that are the counterparts of x and y if we are, talking about the 2-dimensional transformation. So just to translate this notation here, t is the name for transformation. Given by where x is going to be some function of u and v, and y is going to be some other function of u and v. And of course, we can solve for u and v in terms of x and y if we really wanted to as well. But what we're hoping is that by doing this change of variables, that instead of integrating over some weirdly shaped blob, that it's actually more amenable to having more convenient limits of integration after we do that change of variables. Just like in 2 dimensions, instead of integrating an x and y coordinates over, let's say, a sector, well, that sector turns out to be a rectangle in the r and theta variables. So that's what we're talking. That's why, well, at least one reason why we would do that transformation. Let's do a quick example to see what we're talking about here. Talking about sectors. This is example 1. Here, our transformation is given by where x is equal to some function of the variables r and theta, And of course, this is r cosine theta. This is not brand new to us. We've done this many times now. Y is given by some function of theta, h of r theta. Of course, that's r sine theta. So if you were thinking we were going into new territory, sorry to tell you, we've been doing this all along. So if we, on the, using the r and theta coordinates, r goes maybe from 0 to 1, and theta goes from 0 to pi over 2, that would be a rectangle on the r theta plane. On the xy plane, we have the sector, where r goes from 0 to 1, and theta goes from 0 to 2 pi. So what looks like a rectangle in one coordinate system looks like some other shape in the other coordinate system, and vice versa. So that would be our motivation for trying to do that transformation. So I'm just going to move along here. We talked about, you know, what gets mapped to what here. We did this transformation here. These are really just talking about mapping the boundary lines. Let me go back the previous slide here, just to explain. This boundary line right here on the r theta plane, where r goes from 0 to 1 and theta is at 0, that gets mapped to this one on the xy plane. This vertical boundary line on the r theta plane region, that's where r is fixed and theta goes from 0 to pi over 2. Well, that gets mapped to this arc right here on the xy plane, and so forth. C gets mapped to C prime, D gets mapped to right there. Where r is 0 all along this axis right here on the r theta plane. But on the xy plane, r is 0 only at that point. And all the transformations that we could see that sort of mapping of boundary segments. All right, so that's basically what we're talking about here. I'm just going to move along here, unless you have any specific questions. Remember what one-to-one functions are? That basically means that your function does not map anything from the domain to, well, everything in the domain gets mapped to a unique item in the range. That's really what a one-to-one transformation. Now in mathematics, how we prove one-to-oneness is we assume that you have two items in the domain that are exactly equal. And we would have to, you know, say that if two items are the same from the domain, that means that the two items will be the same in the range. So how we actually prove it is so suppose that T of P is equal to T of Q, and then work backward to show that, oh, the only way that T of P could be equal to T of Q is if P and Q are the same thing. Don't worry about that. That's more of an advanced math thing. Just kind of understand what one-to-oneness means. Okay. So, and where the one-to-oneness comes in is in defining the Jacobian. Where if you did not have a one-to-one transformation, then calculating the Jacobian, the Jacobian wouldn't be necessarily would be a unique number. All right, so here's what the Jacobian is. The Jacobian of transformation. Here's the notation of it. They use J. And if it's for two variables, then you use the two variables within the parentheses. Now this is for a transformation where x is written as a function of u and v, y is written as a function of u and v. G is the function for the x transformation, h is the function for the y transformation. And
all the Jacobian is basically this little 2 by 2 matrix that you're taking the determinant of. And within this 2 by 2 matrix, you have these 4 partial derivatives. Partial derivative of x with respect to u, partial of x with respect to v, partial of y with respect to u, partial of y with respect to v. So of course you're taking the determinant, so you're just going to take this times this minus this times this. So it's just going to be basically taking the determinant of a 2 by 2 matrix.
And the result is going to be a function involving u and v, the variables that you're transforming to. So let's do, well, let's actually take a look at this. Let's take a look at where you have x is equal to r cosine theta, and your y is equal to r sine theta. Now, I guess u could be r and v could be theta. So what would be the Jacobian of r comma theta? So this would be the determinant of partial of x with respect to r, maybe partial of x with respect to theta, partial of y with respect to r, partial of y with respect to theta. So here we go. Partial of x with respect to r will be cosine of theta. Partial of x with respect to theta will be what? Negative r sine theta. Partial of y with respect to r is sine of theta. And partial of y with respect to theta will be r cosine theta. And then take the determinant. You're going to have cosine theta times r cosine theta. That's r cosine squared theta. And then minus sine theta times negative r sine theta. So that'll give you plus r sine squared theta. Factor out the r, so you have r times cosine squared theta plus sine squared theta. Of course, that's going to be r times 1, so that gives you r. So r would be the Jacobian for that transformation between the x and y coordinates and the polar coordinates. No surprise there. Now you see where it comes from. And what this is going to tell you, that if you're going to switch from the x and y coordinates to the u and v coordinates, whatever u and v are, then you take that function of u and v, which is what x is, and you put that in for x in the function. And likewise, you replace y by that other function of u and v. And then your dv element gets replaced by your dA with, or dv, or whatever you're using, times the absolute value of the Jacobian. So when we switch like from the xy coordinate to r and theta, the dA element would be the dr d theta, and the absolute value of the Jacobian is the r. So that's why you have an r dr d theta. So we talked about the one-to-oneness. Why it was important to even mention it is that this can only be true here if the mapping between the x and y region and the UV region is a one-to-one mapping. At least for the interior. Not necessarily along boundaries, but certainly for the interior. So let's take a look at example number 2. We already, in fact, we have already done. The example had to do with, example 2 had to do with the polar for r cosine theta, r sine theta. So we've already done example 2. Let's move along here. Example number 3. We are going to be looking at the integral over this region R, this green region right here, of the function square root of 2x times y minus 2x dA. So in xy coordinates. Now,
the region on the xy plane isn't so bad. It looks like
the red line would be something like y equals 2x. The green line would be maybe y equals 2x plus 1. And x would vary between 0 and 2. So the limits for the two variable double integral, at least on the xy plane, wouldn't be too bad. The problem is with the integrand. I mean, yuck. How do you deal with that? Well, you can make this a lot more simple. So you could let maybe u be equal to 2x and let v be equal to y minus 2x. And that would make it a lot more simple. And in fact, what is the substitution that we do? We are going to let x be equal to 2u and let y be equal to 4u plus v. Why are we doing that? Well, if in this first one, if you solve for u is equal to 2x. Now let's see why that would be good. Now, when x, this is x over 2. Sorry about that. I was about to have a little heart attack here. No, that's x over 2. When x is 0, u is 0. When x is 2, u is 1. So that's kind of handy. Now, going over to the second equation, if you replace u by x over 2, we have y is equal to 4 times x over 2 plus v. That means that y is equal to 2x plus v. That means v is equal to y minus 2x. And it just so happens that we've got y minus 2x there as well in the integrand. And oh, by the way, you look on the plane, the region on the plane that we're integrating over is between y equals 2x and y equals 2x plus 1. And if you were to subtract 2x from both sides, you have y minus 2x equals 0 and y minus 2x equals 1. And y minus 2x is what v is. So guess what? V is going to vary between 0 and 1. So u is going to vary between 0 and 1, and v is going to vary between 0 and 1. So it looks like with the substitution, after we plug in 2u for x and replace y by 4u plus v, then the limits of integration for our new integral is going to be where u varies between 0 and 1 and v varies between 0 and 1. So do you see how that's going to be a much simpler integral? So call this integral I. I is now going to be the happy integral. Now replace 2x. Well, 2 times x is 2 times 2u, which is 4u. And replace y minus 2x by v. Now, we've got to figure out what our Jacobian here is. So, what is our Jacobian? So our Jacobian is going to be the partial of x with respect to u, which is 2, The partial of x with respect to v, which is 0. The partial of y with respect to u is 4. The partial of y with respect to v is 1. So 2 minus 0 is 2. So the Jacobian is 2. So we'll plug in 2 for the Jacobian within the integral. And then times du dv. Now, it doesn't matter if we integrate with respect to u or with respect to v, because we're integrating over a rectangle on the uv plane. So we might as well just integrate with respect to u first. U goes from 0 to 1, and with respect to v, goes from 0 to 1. And now this is an easy integral. You can factor out the 2 times the square root of 4. That's 2 times 2 is 4. So factor out the 4. And now this whole thing is going to be 4 times what? The square root of u times the square root of v. So, which is an easy integral. I let you do it yourself because I'm going to move on. So what did that work out to be on the next page? That works out to be 16/9. Look at all the juicy details on page 1058. Okay. So we did a substitution because of the integrand. And in example 4, it looks like, and I'm not going to do very much of this at all, but for this problem here, they're asking us to evaluate this integral. All right, so it's pretty nasty, and we're supposed to integrate it over this diamond region, R. So how in the world can we do that? We would probably have to do 2 separate double integrals, unless we did a substitution. And not only that, this is a pretty nasty integrand, huh? At least with the previous one, we at least had some remote hope of doing it straightforward. This one, you can't even hope to do it in a straightforward way. So you have to do some sort of substitution. Now, and we're integrating over this diamond. This boundary up here is the line y equals x, or x equals y, which means x minus y is equal to 0. This blue line is y equals x minus 2, I think, where it hits the y-axis at y coordinate negative 2 minus negative 2. So, this red line right here is y equals negative x, which means y plus x equals 0. This green line, that's going to be y equals negative x plus 2. So, in other words, y plus x is equal to positive 2. So, if you do a substitution where u equals x minus y and v is equal to x plus y, and you can then see that with these substitutions, then with u and v, you're going to have a rectangle now. Where remember, x minus y is going to vary between 0 and 2. X plus y is going to vary between 0 and 2. And then take this little system of equations and solve for x in terms of u and v, solve for y in terms of u and v. This is just an algebra problem. And then take your Jacobian of partial of x with respect to u, partial of x with respect to v, partial of y with respect to u, partial of y with respect to v. And of course, you could see all the bloody details on there, but the Jacobian worked out to be 1/2. Okay, and then you do the substitution. So everywhere you see x minus y, you can replace with u. And wherever you see x plus y, you can replace with v. So now this is a much more simple integral. And this integrand is something that you can split apart. This is square root of u times hold on here, times v plus 1 raised to the negative 1/2 power. So double integral, that's easy to solve now. And I guess this whole thing works out to be 4 root 2 over 3 times square root of 3 minus 1. Again, check the details on page 1059. Everybody understand what it is that we're doing? And as you flip through the rest of section 14.7, it's more of the same. For example, 5, I'll let you look at that. Here you're integrating over this real crazy region on the xy plane. But of course, if you do a nice substitution, a lot of times the problem is pretty easy to figure out. Either you're told what substitution to make, or you could tell from either the region or the integral what sort of substitution. For example, 5, you're simply integrating y squared dA over this region R. So the integral itself is easy, but the region that you're integrating it over is crazy. It's trapped between these various curves. Here you've got x equals 16 minus y squared for the yellow. For the green one, that's x equals y squared minus 4. And the blue, you got x equals y squared. And the purple there, you got x equals 9 minus y squared. So if you take, like this one up here, x minus y squared equals negative 4. And here you got x minus y squared equals 0. So if you do the substitution, u equals x minus y squared, then you'll see that u is going to vary between negative 4 and 0. And likewise, you could do the substitution, for x plus y squared, both for this curve and for this curve. And you'll see that if you replace v with the x plus y squared, then v will vary between 9 and 16. So making those substitutions using u equals x minus y squared and v equals x plus y squared, you're integrating over this rectangle. And of course, now you know how to do the Jacobian, and you can substitute for y square root of v minus u over square root of 2 times the Jacobian times dA. And that's an easy integral to solve. All right, I'm going to move along here. Let's talk briefly about the three-dimensional change of variables. All right, here's your Jacobian, no surprise. All right, so you figure out your, what you're going to let x be in terms of your new three variables. Same thing for y, same thing for z. Compute your 3x3 grid of partial derivatives. So, and take the determinant of that 3x3 grid. So, for example here,
Who wants some extra credit? Anybody wants some extra credit? Pull out a piece of scratch paper. Put your name on it. So remember that to go from x, y, z to rho t theta and spherical, that z is equal to rho cosine phi, and that x is equal to rho sine phi cosine theta, and that y is equal to rho sine phi sine theta. So what I want you to do is to calculate the Jacobian. Okay, so you're going to do partial of x with respect to rho, partial of x with respect to phi, and partial of x with respect to theta. And then you have partial of y, I should say, with respect to rho, partial of y with respect to phi, partial of y with respect to theta, partial of z with respect to rho, partial of z with respect to phi, partial of z with respect to theta. And then go ahead and work that out. And of course, you should verify that you get rho squared sine phi. So go ahead and give you about 5 minutes to go ahead and work that out. I'll be right back. So we just verified that the dV element for spherical coordinates, it really indeed is the rho squared sine phi d rho d phi d theta, because the Jacobian of that transformation between x, y, z coordinates and spherical coordinates indeed gives us that rho squared sine phi. In fact, it might even be a minus rho squared sine phi, but when you take the absolute value, you just get the positive. Okay. All right, so the rest of this section talks about the change of variables in 3 dimensions. All right, I'm going to let you take a look at that. We're going to go ahead and move forward. And we are now in chapter 15. We have now moved beyond multiple integration. And it's time for us to now think about integrating and a vector field. So in section 15.1, we're going to talk about vector fields, which is unlike anything that we've really talked about, except we have been talking about vector fields, but we haven't really been calling them vector fields. But now we could actually say that the gradient is an example of a vector field. The gradient of a vector. So what is a vector field? Well, we like to use them a lot, especially in physics and engineering. So imagine either on the 2-dimensional plane or in 3-dimensional space that if you tell me the coordinates of your point, I can attach a vector to it. And the magnitude and direction of that vector could very well be dependent on the coordinates of the point. And you string all those vectors together, and that vector field could potentially tell me the path or the current of wind or electricity or magnetic field or anything, or whatever. In meteorology, we could use vector fields to, plot a thunderstorm with its various wind currents. Or we talk about temperature diffusion on a surface, where the arrows point in the direction of heat diffusion from hotter to cooler regions. Or maybe a magnetic field, maybe going from higher potential to lower potential or whatever, from positive to negative or whatever. Now, the two-dimensional vector field mathematically is going to look something like this. It's a combination of being a multivariable function and also being a vector. We oftentimes will like to use capital letters like capital F as the name of our vector fields, but they're going to be boldened, at least in the textbook or on written page. Now, in our own handwriting, of course, we would just use the traditional overhead arrow to indicate that that is indeed a vector, but it is going to be dependent on knowing what the x and y independent variables are. So you could use the component form or the I hat, j hat form. Hey, after all, it's a vector. But each of the components of your vector will be functions of x and y. We could talk about your vector function being continuous, differentiable, only if the component functions are differentiable and are continuous, respectively. Here's an example of a vector field given by 2x, 2y. Now notice at the origin there's nothing, right? But you move away from the origin, like for example at 0, 1. At 0, 1, the vector field is 0, 2. So no kidding, your vector is going to point straight up. At 0, -1, your vector field is going to be 0, -2. So no kidding, your vector is going to point straight down. At -1, 0, your vector field is -2, 0. So your vector is going to point that way and so forth. And of course, the further that you go away from the origin, the higher the magnitude that your vector is going to be. So there's an example of a radial vector field where all the vectors are pointing directly away from the origin. What is the magnitude of this vector field? Well, square root of 4x squared plus 4y squared. Moving along here. Here's another vector field. This is example 1, part A. A shear vector field where one of the coordinates is just set equal to 0. Meaning, I'm sorry, not coordinate, but one of the components is set equal to 0. And then if it's the first component set equal to 0, then the second component is set equal to the first variable. So if you wanted a horizontal shear vector field, then you could have y comma 0. But here you have a vertical shear vector field, so you have 0 comma x. What is a shear? Who's a mechanical engineering student? So what does shear mean?
Going in opposite directions.
There you go.
Any aeronautical engineering students? What does wind shear mean?
Wind shear?
Yeah.
It's change in wind direction or speed.
Yeah. So yeah, so a vertical change in wind velocity.
Yeah,
Huh?
it's like you look more for speed.
Yeah. So it's kind of so. Are there any pilots in the room, or anyone? Know, yeah. So the wind shear is kind of a big deal for, especially when you're landing and taking off. Huh? Yeah.
Did this ever say if that had something to do with the San Francisco incident, girls?
There's lots of speculation, but
Yeah.
he was just flying way too low and slow. That's just
Oh, yeah.
what it comes down to it. Exactly why that is true, we don't know yet. I don't know. I try not to follow the news too closely because there's a lot of speculation out there. Now I've been reading. Oh, it's because of Korean culture, because of the deference to authority figures in the cocktail and stuff like that.
They said one of them got hit by a first responder.
Oh well, one of the people who died, one of the Chinese girls that got thrown out of the airplane, that she got ran over by like a fire truck or something.
So she survived the plane crash, but then
Yeah.
she got ran over.
Yeah,
It's not your
that's
name.
horrible.
Not your name.
Yeah, her name isn't Lucky. So anyway, here's yet another vector field here, called the channel flow. For obvious reasons. And of course, we know that when water is flowing through a pipe, that the fastest velocity is going to be right down the middle, and where the water or the liquid interacts with the side of the tube, it's going to slow down a little bit. So there's the general form, channel flow for horizontal, or 0 comma 1 minus y squared. If you want vertical channel flow, in 2 dimensions at least. Here's your rotational vector field. So if you want to model a hurricane, and it's actually a pretty simple form. Negative y comma x, and of course then you can put in scalar multiples if you want to really make the wind speeds more pronounced as you get further away from the origin. Now this one happens to be going counterclockwise. How could you jigger this to make it go counterclockwise? Oh yeah, to make it go clockwise. Maybe you can go y comma negative x. So. All right. Now, radial vector fields are pretty important. Like the gravitational fields, your electric fields, and so forth, are all radial sort of vector fields. So we saw an example of radial vector field where the vectors are always pointing directly away from the origin, and there are some radial vector fields where they all point directly in toward the origin as well. And they all have this sort of form here, where you've got R, but what is R? R is just basically your radial vector either pointing away or inward toward the origin, divided by magnitude raised to some power. So I'm going to flip the slide here to take a better look at this. Now, the R vector is simply x comma y vector, in case you were wondering what that was. They don't specifically mention it, but They say it's for all these outward facing ones, but like I said, there could be a negative for others, so we have to, they don't really talk about it in this part of textbook. That's okay. But when you have this radial vector divided by some power of the magnitude, then that's a radial vector. Now, if you were to separate one factor of the magnitude, and you have r divided by magnitude r, then that's going to give you your unit vector pointing away from the origin. And then that means that the 1 over magnitude r raised to the p minus 1, whatever p is going to be the scalar multiple. So think about it. What is the, say, the gravitational field? That's an inverse square field, isn't it? So you double the distance, and that means that you have 1/4 the gravitational attraction. Huh? For example. So what would you have? You would have P being equal to 3, huh? For the inverse square fields. Let's take a look at example number 2 from section 15.1. All right, so we have a circle C. And that's the circle x squared plus y squared is equal to a squared. So circle of radius a centered at the origin. And we're going to do 2 parts to this example here. Part A, show that at each point of the circle, the radial vector f is equal to r over magnitude r. So let's go ahead and write that down. Vector field f is equal to r over magnitude r. Is orthogonal to the line tangent to C at that point. Now r, of course, is the vector x comma y. And the magnitude is square root of x squared plus y squared. Now, this being a radial vector field, you see the light blue vector right there? Vector field x, comma y, is going to be pointing directly in. Okay, so now what is it we're supposed to find? We're supposed to find that vector field f vector is orthogonal to the line tangent to C at that point. Now, I got a question for you. What do you remember about the relationship between gradient vectors and contour lines? What's that relationship? Are they orthogonal or not? Right? So if you've got the equation g of xy being equal to some constant, all right, that's going to define a contour curve, huh? So then if you then take the gradient of g and evaluate that gradient at some point on the contour, then that gradient vector is going to be orthogonal to that contour curve. What was the equation for the circle? Well, it's x squared plus y squared equals
R squared, okay, so, or A squared or whatever. So, we have x squared plus y squared is equal to a squared. And let x squared plus y squared be equal to our g of xy. And what is the gradient of g? Gradient of g is equal to what, 2x comma 2y. And of course, that is going to be parallel with the vector field function. Because after all, you factor out the 2. Here, you got x comma y. Up here, you factor out the 1 over square of x squared plus y squared. You have just the x comma y. So that's why you have these two vectors being parallel with each other right here. And we've already established that the gradient vector is orthogonal to the contour curve, huh? And x squared plus y squared equals a squared is a contour curve for whatever the function x squared plus y squared is. Okay? Because of that orthogonality, that means that the gradient vector, and hence vector field F, will be perpendicular to a tangent line. So that right there is enough to show what we needed to for part A. Does that make sense, everybody? What does part B ask us to do? Show that at each point of C, the rotation vector field x comma y is parallel to the line tangent to C at that point. Okay. Well, how can you find out whether two vectors are parallel? You know how to do that? If I ask you, is this vector parallel with that vector? How can you tell? Well, cross product, if the cross product works out to be 0, then that's one way. Or if you could just simply show that that one is a scalar multiple of the other. And if we want to show that something is tangent to C, so tangent to the curve, well, another way is to take the dot product of with a vector that we know to be orthogonal to the curve, huh? So for part B, we've got g of x comma y given by this is a rotation vector field, negative y comma x divided by square root of x squared plus y squared plus y squared. And we're supposed to show that these vectors are parallel with the circle. How can we do that? Well, just by taking the dot product of F. So we know vector field F is orthogonal to the circle. Huh? Does that make sense? So what happens if you take big G dotted with big F? Never mind the 1 over square root of x squared plus y squared. You get negative y times x plus x times y. And you get 0, huh? And that right there is enough to show that this vector field, big G here, is going to be parallel with the circle. So that right there is enough to show that big G, it really is a rotational vector field.
that goes around in a circle.
Okay. Any questions on what we did? So now you know how to show that a vector field is parallel or perpendicular with something, huh? The big thing is to remember that the gradient of a function can be thought of as being, giving you a vector field that's orthogonal to a contour line or a contour surface or something. Okay, important relationship to understand. Let's now step it up to vector fields in 3 dimensions, where at any point in the x, y, z coordinate system, you have your vector field, whose direction and magnitude is determined by x, y, and z, as given by these functions little f, little g, and little h. Of course, it's hard to draw in 3 dimensions, and it's especially tough to do 3-dimensional vector fields. But on a computer algebra system, you could do it, and you can visualize, you could twirl it around and see those little arrows coming out at you and stuff. Pretty cool to look at. Oops. Sorry about that. So here's an example of a 3-dimensional vector field. Here we've got big F being equal to x comma y comma e to the negative z. Now, here we've got x coming down like that. We've got y going that way. We've got z going up. Z's actually going more like this, tilting over like that. Now, big thing I want you to realize that the larger that z becomes, the smaller that e to the negative z becomes. So the further up that you go, the more flattened those vectors are going to become, because e to the negative z becomes relatively small for large values of z. So for further up, vertically you go, those arrows are going to be almost horizontal, almost parallel with the xy plane. Of course, for small values of z, then the z component is going to be relatively large. Okay. If you were to look at this vector field from up here and looking downward like that, then this is what it would look like. Here's another 3-dimensional vector field. This time we've got a pipe or a tube with fluid running through it. And you can model this vector field with, or model this phenomena of fluid going up through the vector field with this sort of vector field here, 0, 0, 1 minus x squared minus y squared. But if you like cylindrical coordinates, 1 minus r squared. Now, if we had more time in the semester, I would love to talk to you about vector fields and spherical coordinates and cylindrical coordinates, but that's more of an advanced topic, so we typically don't discuss it in Calculus 3. But if you want a reference, I can give you the reference. All right, moving along here. Again, just as a reminder, gradients are orthogonal to your contour lines. And which way do they point? Uphill or downhill? So if this were temperature, for example, would the gradient vector be pointing toward the direction of maximum increase or the maximum decrease? Did you guys talk about that with Dr. Wu? If this were, say, a contour map, would the gradient be pointing downhill or uphill?
Uphill.
Uphill, exactly. The direction of steepest ascent.
So if you're standing here on the trail and you want to get up to the top of the mountain most quickly, and you don't care about how steep it is, but you just want to know how, what is the steepest climb that I can make, well, just follow the gradient. The gradient's going to point the way. So if you point out your compass, and your compass, instead of giving you cardinal direction, it tells you the gradient, well, follow the gradient. That'll take you uphill quickest. So what would the negative of the gradient be for you? The negative of the gradient will give you the direction of steepest descent, the quickest way downhill, which a lot of people would be interested in. So when you take the gradients of a scalar function, the result is going to be, well, a gradient, but a gradient is also a vector field. We, in this context, are using phi as a 2-variable or a 3-variable scalar function. And then we take the gradient of that function, and the result is going to be our vector field. And now, if it turns out that that vector field is the result of taking the gradient, then we call that vector field a gradient field. And where the function that you took the gradient of is said to be the potential function. Now, one of the challenges that we're going to have later on in the chapter is, okay, whether or not we are dealing with a vector field that happens to be a gradient field or not. And we'll be able to talk about a test to determine whether you have a gradient field or not. But if I just, boom, give you this vector field, would you be able to tell me whether it's a gradient field? We'll see. But not today, though. Let's take a look at example 4a. On page 1076. Here we've got the temperature on a metal plate being a function of x and y being given by 200 minus x squared minus y squared. So basically what this says is on this circular metal plate of radius 5 units, that right at the origin the temperature is 200 degrees. And that the further you go away in a radial fashion from the origin, the temperature is going to decrease. So if you want to convert over to rectangular coordinates or polar coordinates, you have 200 minus r squared. So when you're total of 5 units away, 5 squared is 25, 200 minus 25 is 175. So on the edge of the plate, you're at 175 degrees. Let's go ahead and calculate the gradient of the temperature. And of course, you'll have negative 2x, comma, negative 2y. And so this is a negative radial function, which means that those arrows are going to be all pointing toward the origin. Which should not be a surprise for 2 reasons. Number one is that we know that the gradient always points in the direction of steepest increase of the function. So they're all going to be pointing toward the hottest point in the plate in the most direct fashion, which is the center of the plate. And then second of all, if you were to set the temperature equal to a constant and then take the gradient of this, well, not the gradient, but just understand that for constant temperatures that you have these various circles. So the level curves of the temperature function is going to be these concentric circles. And that the gradient vectors are going to be orthogonal to those circles.
So it shouldn't be a surprise of that relationship between those gradient vectors and those level curves. So this was part A, where we just needed to talk about what is the gradient and the level curves and stuff. Here's part B. Sketch and interpret the gradient field associated with the velocity potential. We've got phi is equal to arctangent y over x. So without looking at the example on your scratch paper, go ahead and calculate the gradient of phi of arctangent y over x. Go ahead and do that. And then check your answer in the example. So go ahead and calculate the gradient of that function. What do you get? So what is the gradient of phi? So of course that's going to be partial of phi with respect to x I hat plus the partial of phi with respect to y j hat. So we know that the derivative of the arctangent function is going to be 1 over 1 plus the argument squared, and then using the chain rule, the derivative with respect to x of y over x, which is going to be a negative y over x squared, I hat, plus, and then the derivative with respect to y, so you still have 1 over 1 plus y over x squared, times the derivative of y over x with respect to y, which is 1 over x j hat. Now, to make it simple for the second one, we can replace x by x over x squared. So then we have negative y over x squared plus y squared I hat plus x over x squared plus y squared j hat. So in other words, we have negative y comma x over x squared plus y squared. So because of that negative y comma x, we know that that's going to be a rotational field. Now, the potential function is arctangent y over x. And if you set that equal to some constant, then what do the contour lines look like? Well, arctangent y over x equals c means that if you take tangent of both sides, you get y over x is equal to tangent of your constant c, which is some other constant, call it k. So that means that y is equal to some constant times x. Depending on c, which then determines k, we just have some line that goes through the origin with slope k. So the contour lines of the arctangent of y over x are just going to be these lines that go through the origin, which happen to be orthogonal to these vectors from the vector field, huh?
which are from the gradient field. So it shouldn't be surprised that the contour lines are orthogonal to the gradient field. Very, very important to
Remember, we've said it many times now. A special relationship. Here we're just talking about the equipotential curves that says that if you've got a contour map with all these contour lines,
like, and this kind of a generic sort of map anyway. Well, these red curves that you see here are basically just conglomerations of gradient vectors that shows the flow. Maybe in the direction of maximum increase, so maybe it's climbing out of the extreme low values of function uphill or something. So if you want to know if you're standing right here, in what direction do you need to go in order to maximize the function in the steepest direction, then you go this direction, then try it again. You reevaluate your gradient to tell me the new direction, and then go a little bit more in that direction and so forth, and keep updating it. So these red curves are called equipotential curves, and they are always going to be orthogonal to the contour field, contour curves. And see these gradient vectors, they're always going to be tangent to those equipotential curves.
okay. So we've got one last example to take a look at before we part ways this evening. And here, for example 5, we're going to take a look at phi of xy, this potential function, being equal to 1/2 times x squared minus y squared. Now, when you set this function equal to
Various constant values.
let k be equal to some random constant, and then of course multiply both sides by 2, so you have x squared minus y squared is equal to 2k. Or in other words, x squared over 2k minus y squared over 2k is equal to 1. So it shouldn't be a surprise
For you to discover that, oh my God, this is the equation of a hyperbola. In fact, it's a whole family of hyperbolas. You tell me k, and I'll tell you the hyperbola. For different values of k, we'll have different hyperbolas. So if k is equal to 2, then this right here, as well as this one, are two branches of that contour curve hyperbola. If k is equal to 1, then this branch together with this branch is a different level curve. If k is equal to 1/2, then here's your two branches. If k is equal to negative 1/2, here's your two branches of your hyperbola. K equals -1, k equals -2, and so forth. So you got your family of level curves. Now, going across orthogonal-wise across your contour lines will tell you the general direction of your equipotential curves. Except, do you know that you're going to go from up here down there or in the other direction? Well, of course, all you need to do is to take the gradient. So you take the gradient
of that potential function. Oops. Well, anyway, we're going to keep that. Go go back down here. Now, if you take the sorry about that. Take the, sorry. I need to turn on my pen, that's all. Take the gradient of phi. Anyway, you get x comma negative y. And so this is going to be what tells you that it's going to be in this direction, for example, if you're in the first quadrant, the direction of your equipotential curves. And if you're in the second quadrant, then the x coordinate and the y, x coordinate is going to be negative, y coordinate is going to be positive. So the direction is going to be in that direction for your equipotential curve. So you know this curve is going to cut across orthogonal wise. You know, just like you'll have an orthogonal trajectory like across here, across here, across here. But you want to know the direction of the flow, of your equipotential flow, just plug in your x and y coordinates into that gradient vector. And that's going to point in the direction of your equipotential flow. So that's it. When we come back on Tuesday, we're going to start looking at line intervals. Kind of a fascinating topic. We know how to integrate along the x-axis, right? We even know how to integrate along the y-axis, right? But what we're going to look at is, imagine in 3 dimensions that we've got some curve on the xy plane. And of course we've got some function f of xy whose graph is some surface. So what we're going to take a look at is integrating along some curve, generalized curve on the xy plane, finding the area that's below the curve, below the surface and along that curve. Also, we're going to be integrating in vector fields. So it's going to be really fascinating. I think that you'll enjoy it. So have a good night, and I'll see everybody on Tuesday.